All right, everybody. Um, so we met vertical asymptotes of rational functions. Now let's talk about horizontal asymptotes. These are kind of horizontal lines that the graph of our function might kind of hug towards as x gets very large, going to positive infinity, or as x gets very small, going to negative infinity. So here is an example of a horizontal asymptote, actually a function that looks like two horizontal asymptotes. It looks like it has the line y equals 5 as a horizontal asymptote as x goes to positive infinity, but the line y equals to 0, alias the x-axis, is a horizontal asymptote as x goes to minus infinity. So I think that's the most number of horizontal asymptotes that a function could have is 2. We'll find out today that rational functions that we've been studying can have at most 1. So here's an example of that where we have just the line y equals to 0 is a horizontal asymptote. So looks like as x goes to infinity, the y values get closer to 0, and as x goes to negative infinity, the y values also get closer to 0. So how do we find the horizontal asymptote of a rational function? Well, remember, a rational function is a fraction of polynomials. And so everything here is going to depend on the degrees of those polynomials. So let's say f of x is p of x divided by q of x. So we can say p of x is the numerator, q of x is the denominator. Then if the degree of the numerator is smaller than the degree of the denominator, the horizontal asymptote will be y equals to 0. So it looks like this could be an example of that happening there. So if the degrees of p of x and q of x are equal, then the horizontal asymptote will be the ratio, y equals to the ratio of the leading coefficients. So maybe we should stop here and remind ourselves, what is all of this stuff? What is degree? What is leading coefficient? It's been a while, right? So a polynomial, right, is a sum of powers of x, right? And the degree of a polynomial would be the highest power of x that occurs. So something like 5x squared minus 4x plus 1 is a polynomial of degree 2 because it has the highest power of x that occurs is x squared, right? Now, what is the leading coefficient of a polynomial? Well, that's the number that multiplies that highest power of x. So in the example that I just gave of 5x squared minus 4x plus 2, then 5 is the leading coefficient. So if we have a rational function where the degree of the numerator and denominator are the same, then we get the horizontal asymptote by looking at the line y equals to the ratio of the leading coefficients of the numerator and denominator polynomials. Okay, and last but not least, if the degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote. So it is possible for us to have a rational function that does not have a horizontal asymptote. And the notes say here that there is actually a slant asymptote. Well, what I think of as slant asymptote is a line which is not a horizontal line. So it's a line with non-zero slope. And we will have one of those, but that's only in the case when the degree of the numerator is exactly 1 more than the degree of the denominator. And we will see an example of this before this video is over. Okay, and so as we said here, rational functions have only one horizontal asymptote. Okay, so maybe we'll do some examples now and determine what some horizontal asymptotes of some rational functions are. So let's consider the function f of x equals to x plus 4 divided by x squared minus 3x plus 8. It looks like the degree of the numerator is 1, since we have x to the 1 plus 4. And the degree of the denominator is 2, since we have x squared is the highest power of x that occurs there. So this abides by, I believe, the first rule above. The degree of the numerator is smaller than the degree of the denominator. So the horizontal asymptote is y equals to 0. And you can see the idea here is that as x gets really large, as x goes to infinity, x plus 4 is going to be smaller than x squared minus 3x plus 8. The sort of thing that dominates is this x squared on the bottom. And so if we have something big that's divided by something much, much bigger, then that value is going to tend to 0. Okay. The next example has f of x equals to 3x squared minus 3x minus 4 divided by 9x squared plus, or sorry, 8x squared plus 9x plus 1. It looks like here the degree of the numerator and denominator are both 2. So our horizontal asymptote will be the line y equals to 3 divided by 8. Those are our leading coefficients, 3 on the top and 8 on the bottom. And again, the idea here is that as x goes to positive infinity or negative infinity, these smaller terms here, 3x minus 4 and 9x plus 1, they don't have as much significance as 3x squared and 8x squared. The squaring part dominates, in a sense, this linear term. So we can forget these linear pieces and just be left with 3x squared divided by 8x squared, which might simplify to like 3 over 8 in a sense. Okay. The last one here has f of x equals to x squared minus 3x plus 5 divided by x minus 1. And it looks like the degree of the numerator is 2, but the degree of the denominator is only 1. So by rule number 3 above, I believe, this function has no horizontal asymptote. But we can see that the degree of the numerator is exactly 1 more than the degree of the denominator. So there will be a slant asymptote, a non-horizontal line, a line with some non-zero slope that this function sort of approaches or hugs against as x goes to infinity and as x goes to minus infinity. So how do we find that? Well, we'll find it by polynomial division, right? This rational function is nothing but what looks like polynomial division. So let's go ahead and do that polynomial division. Now notice here, you're allowed to do synthetic division since we have something x minus 1 is the divisor. I'm going to not do synthetic division because I think it kind of hides exactly what's going on, and I want everything to be as clear as possible in these videos. But yeah, feel like you are totally allowed to do synthetic division if you like that. So here I'll write x squared minus 3x plus 5, and I'm going to divide that by x minus 1. So I have to put something up here such that when I multiply it by x, I can cancel out x squared and get x squared down here. Well, that is x, because then x times x gives me x squared. And then x times minus 1 gives me minus x. And now I will subtract this entire expression from that which is above it. And so x squared minus x squared goes to 0. That's perfect. And then minus 3x plus x becomes minus 2x. And then we will bring down this 5 here, and rinse and repeat, right? So now I would like to cancel out this minus 2x. So I'd like to put a number up here such that when I multiply it by x, I get minus 2x. Well, I've already put it there, so you can see it is minus 2. So minus 2 times x gives me minus 2x. And then minus 2 times minus 1 gives me plus 2. All right. So then let's do this same thing. We'll subtract this entire expression from that which is above it. So we'll have minus 2x minus minus 2x. That gives me 0. And 5 minus 2 gives me 3. And so this step was almost a little bit overkill if we were just asking for the slant asymptote in this case, because now that we have this guy, x minus 2 as the quotient, that is going to be our slant asymptote. So y equals to x minus 2 will be the slant asymptote. Now, what happens to this 3? Well, I probably should have written this here, and I can explain this more when we meet in class, is that if you want to write this division now, you can write that x squared minus 3x plus 5 divided by x minus 1 equals to x minus 2 plus the remainder 3 divided by x minus 1. And so as x goes to infinity, the term that has 3 divided by x minus 1, that goes to 0. And the only thing that's left over that matters is this x minus 2. So we'll say more about that when we meet in Zoom, I guess. Or if you want to email me, that's also fine too. Okay, so rational functions, I think we talked about this before, they don't cross their vertical asymptotes because those are places outside the domain. But they are allowed to cross horizontal asymptotes or slant asymptotes. So what's going on there? Well, they won't be crossing them like out at infinity. They'll be crossing them maybe possibly somewhere kind of in the middle. So what would that look like? Let's do this example to see what's going on. So we have this rational function x squared minus 3x minus 2 divided by x squared plus 1. It has degree of the top and degree of the bottom both equal to 2. The leading coefficients are both 1, and thus the horizontal asymptote is y equals 1 over 1, or just 1. Now, what would it mean for the rational function to cross its horizontal asymptote? That would mean that the lines given by y equals 1 and given by the graph y equals f of x would intersect each other. So in particular, we would have to have that f of x equal to this horizontal asymptote y value 1. Okay, so we can now set up an equation there. We'll have x squared minus 3x minus 2 divided by x squared plus 1 equals to 1. And we can multiply both sides by x squared plus 1 to get rid of the fractions. And that leaves us with just x squared minus 3x minus 2 on the left, and now x squared plus 1 on the right. Okay, and now the x squareds cancel, and we're left with just minus 3x minus 2 equals to 1. We can add 2 to both sides and get minus 3x equals to 3, or x equals to minus 1. So it looks like this graph, f of x, or this graph of y equals to f of x, does cross its horizontal asymptote at the x value x equals to minus 1. The full point would be x value is minus 1 and y value is 1, right? Okay, so stay tuned. In the next piece, I think we'll do at least 1, maybe 2 examples of graphing rational functions. It's a little bit of work, but it is a good exercise to keep us strong. So we'll see you then.